Okay, so what I'm going to talk about, there's a framework which appeared, I guess it all started like 3 years ago, where mixing bounds or expansion bounds are proven using technology coming from high-dimensional expanders. This is kind of started, I guess, by a work by Nima Anari, Liu, Liu Oveis Gharan, and Cynthia Vincent, who used high-dimensional expanders to show that matroids have a spectral gap. And this work of theirs kind of pushed a to my opinion, really interesting series of works, which are all kind of based on this technology of high-dimensional expansion. And the goal of these talks is more or less going to be to give an alternative approach towards most of the things that they're doing. So without any high-dimensional expanders, that they're going to be replaced by mostly like simpler, arguably martingale arguments. And yeah, so today what we're going to do is basically give a framework and show how it recovers at least one work due to, so today is mostly after the work by Anari, Nima Anari, Liu, and Liu Oveis Gharan from, I guess, 20. And all of this is going to be joint work with Yuan Zichen.
So maybe ask the audience if they can see the red color.
I think the light would be better for me.
Okay, I'll use light for now. Okay, so
recording of, yeah.
What's our ultimate goal? Our ultimate goal in all of the results we present is going to be the following. We have some measure either on the discrete hypercube or on Rn. So given probability measure mu on omega, and for us, omega will be either -1 to the n, the discrete hypercube, or just Rn. The framework works for more examples, but we're going to focus on this. And given this, we want to efficiently sample from the measure. Okay. So this is what we'll be interested in, and to kind of get you into business, let me start from some examples of such measures that we might be interested in. So examples, the first example is what's called an Ising model. We have some graph G, and we think of its vertex set as just numbers 1 to n. And so given G and given a positive number beta, we define a measure mu sub G and beta, a measure on -1, 1 to the v, which is going to be defined by the following formula. So the density at the point x is going to be proportional to x of the sum u and v in the vertex set of x sub u, x sub v, times beta.
Supposed to be the edge set, right?
Sorry. In the edge set, x sub u, x sub v. So whenever, for every edge, we have a bigger measure if the two sides of the edge agree with each other. So we think about it as follows. I guess most of you have seen it, so we'll do it quickly. We have the vertex set on the graph. On each vertex, I have either a plus or a minus. And whenever two vertices are connected by an edge, the bigger beta is, the more incentive they have to agree with each other. Okay, so this is called an Ising model, and there's a lot. I mean, there are some people here who know it much better than I do. There's a very, very deep theory on Ising models on lattices, for example. But you can basically take any graph. Okay. And okay, this gives us a measure on the discrete hypercube, and we might want to sample from it. Okay, this is the first example. Example 2. Omega is Rn, and mu is just a measure with a convex potential, namely nu of x, d nu of x is e to the minus some convex function v of x dx.
Why should I think about sampling from nu? So that would be like the analog of calculating the averages, calculating all kinds of probabilities using this sampling method.
I mean, it's, if you can sample, you can calculate averages. Turns out that also the other way around. But I mean, I just want to produce a sample from a point distributed approximately according to the measure. Okay. This is the second example to have in mind. This is called
typical configurations.
This is called a log-concave measure. Third example. Again, we have graph G, and let's denote by I sub G as the subset of, as the family of subsets of the vertices which are independent.
So maybe Ronen, maybe you want to say about the second example that it includes as a special case computing the volume of convex bodies in high dimensions.
Right. So I mean, it includes as a special case sampling a uniform point from a convex body in high dimensions. And if you can sample, you can do PCA, you can compute the volume. That's not very obvious, but there's a very nice reduction. Right. We're not going to talk so much about how to apply. I mean, there's a lot to say, but for us, let's just think of sampling as the ultimate goal. Okay. So let's consider the family of independent sets, and suppose that, and now nu of x, suppose that it's proportional. So again, x is in -1, 1 v. Is the indicator that x is an independent set times some parameter lambda to the size of x. So maybe let's do a little abuse of notation. Okay, this is a pretty bad abuse of notation. Maybe, I don't know, a usually denote it by this, which is just, you know, the number of vertices that I have selected in X.
Yeah, you can put it 0, 1 to the V, and then it will be pretty clear.
Yeah, but I want to be consistent with, yeah.
So this is the hardcore model.
So this is called the hardcore model. I didn't write it. The reason it's called hardcore is, you know, I have a graph and I have some sites, and some sites can have particles in them and some sites cannot. And these are like hardcore particles in the sense that if there is a particle here, there can't be any particle adjacent. They like repulse each other in a, like, you know, in a way that can't like compress or whatever. Yeah. So this is the third example, and the fourth example to have in mind is very close to, it's still called an Ising model sometimes, only I have like weights on the edges. So given J and n by n matrix that we call an interaction matrix, and H in Rn, which we sometimes call an external field, mu of J and H at X will be proportional to e to the, there's usually a minus, but let's not put it, 1/2 xj x. Maybe let's even omit the 1/2, it doesn't matter too much, plus h dot x. So it's pretty clear that by taking J to be some constant times the, you know, adjacency matrix of the graph, this is just a generalization of this, okay? And one model that we'll look at later is the Sherrington-Kirkpatrick model. Or SK model, where J is just, Jij is just some, those are IID Gaussians centered and with variance beta over n, I guess. So just all the interactions between particles are IID Gaussians. So we're thinking about it. I first generate these Gaussians, then I have, my model is fixed. I've already randomized these Gaussians. And now I have the extra randomness. I basically have a random probability measure on the discrete hypercube. And we want to sample from it. Okay. Good. Any questions so far? Good.
Magnetic field constant, or what are you going to do with the H?
The H, let's say it's just 0 or it's random, or yeah, usually people think of some constant times the all ones. For now, I just, you know, want you to have these examples to just keep in mind. I'm not really saying anything at all. Good. So how do we actually, you know, what's the most common paradigm about how you actually sample from these? Well, the most obvious, perhaps, thing to do is to try to use a Markov chain. Find a Markov chain whose stationary measure is the measure you want to sample from, and hopefully you can run the Markov chain for a time that's not too long, and this, you know, what you'll have is a more or less a sample from your measure. Okay.
And it shouldn't be too long because the graph itself, the Markov chain, will have exponentially many points in it.
The graph, exactly. The Markov chain is a Markov chain on this. So it has exponentially many points in the state space, right? And, you know, so it could be a priori that it takes exponential time to converge. And we're interested in the cases that it doesn't. It takes polynomial time. Good. So we'll start now with only 2 examples of Markov chains, but we'll see some more later. First example is the so-called Glauber dynamics. So Glauber dynamics is a Markov chain associated with any measure on the discrete hypercube in the following way. So let me just think about it as, so let me first like give you an example, describe it on an Ising model. So suppose we have a graph and we want to sample from the Ising model. So we start from some state, I don't know, maybe everything is a minus. And one step of the Markov chain is the following procedure. We first uniformly pick a vertex from the graph. Suppose we picked this vertex. And then we refresh the value of this vertex according to its conditional distribution, where we condition on the rest of the sites. Okay, so we basically condition on the values of all the other vertices. This induces basically it induces 2 probabilities. The probability for this thing to be a plus and a minus, and we just refresh it. We toss the coin for this one. And then, you know, maybe we got that this is a plus. And now we, again, uniformly choose a vertex, maybe this one. And we refresh it, and so on and so forth. Okay, so what I described is relevant for any measure on the hypercube. So, for any.
So when the 2 probabilities are.
This is a bad color, probably. Yes.
Yeah, so just to be clear, you're saying, okay, you start with some x, with some x configuration on the hypercube, and then you have like, I don't know, x naught, which is changing.
I start with a point in the hypercube. Let me actually describe it here, and I think it'll be clear. Okay. So first of all, Glauber dynamics is basically a mapping from probability measures on the hypercube to Markov kernels. So let's call it PGD of mu. So this is just an operator from functions or measures on the hypercube to measures on the hypercube, okay, which describes the basically transition kernel of the Markov chain. And well, it's defined by the transition from a point X to a point Y is going to be equal to, first of all, the indicator that X is a neighbor of Y. So every time I only refresh one coordinate, meaning that, you know, the next point is a neighbor in the hypercube. And then I basically need to put here the probability to choose Y, the neighbor, conditioned on all the rest. So this is just the measure at Y over the measure at X plus the measure at Y. So basically, once I chose, suppose I'm at a point X in the hypercube, just to. So now these are not sites, these are vertices of the hypercube. Suppose I'm on this vertex, I first choose which coordinate I refresh. Then perhaps I chose to refresh like this coordinate, the up-down coordinate. So now my next type will be either this or this. The probability to be this is, the measure of this over the two measures. The probability to still be this is, mu of x over the sum of measures. Okay. So this is called Glauber dynamics. And it's pretty easy to see that the stationary measure, so it really, by definition, it follows that for all x and y, we have that mu of x times the probability to go from x to y is equal to mu of y times the probability to go from y to x. So I wish I hadn't erased this picture. So this you can immediately check from here. And well, basically what it says is like, you can think about this as a flow. The flow on this edge going to this side is, the probability is whatever mass I have here times how much of it goes to here. It's equal to the flow on the other side, to the other side.
That's a reversible.
Meaning this is called reversible, and it's clear that the stationary measure is going to be nu, right? Because if I start from nu, I'm transporting the same amount of mass over every edge in both directions. So I'm going to remain nu. Okay, this is very natural kind of property for Markov chains. I guess I'm writing way too big. Running out of boards too quickly. So this is Glauber dynamics, and we have like natural counterparts on Rn. So on Rn, I'll just give you one example called the Gaussian walk. Where the probability to go from x to y is proportional, actually it's equal to e to the minus, let's say, some alpha x minus y squared, maybe let's say alpha over 2. 1/2 sigma squared. So I have a parameter sigma, which is like the variance of the Gaussian. I have the normalization constant, which I'll probably get wrong. And so if I'm at a point, I choose a Gaussian step, but I can't just do a Gaussian step because then my stationary measure will be just, there will be actually no stationary measure. This is kind of like the heat equation. So I'm going to add a term that looks exactly like this, which will make it a reversible Markov chain. So I'm just going to take here mu of y over mu x plus mu y, where, I'm kind of abusing notation. These are going to be the densities of the measure. Okay. So this is a natural counterpart of Glauber dynamics, and we might want to use it to sample for a measure in Rn. Questions?
Yeah, what's a reversible Markov chain?
This is what I wrote here is the definition of a reversible Markov chain. It's a Markov chain that's like on every edge has like the same amount of mass going in both directions.
You can think of a random walk on an undirected graph. That's the best example, simple example of reversible.
Right. It's in a sense, it's like a non-directed Markov chain. Like there is no preferred direction between any two sides. Yeah. Okay, good. So you can say, okay, great, we can sample from any measure now. But our point is going to be now to establish, bounds on how long it actually takes to sample. And And I'm gonna wave my hands just a little bit right now to convince you that in some cases, there is like a natural obstacle to those chains mixing quickly. Okay, so there is a natural obstacle to fast mixing. Which I guess I'll call it non-uniqueness. So this is only going to be on a very intuitive level, but I mean, we can make
Fast mixing meaning that you start with any point that you want on the cube and you get in
yes,
time to.
yes, I'll define it, you know, more precisely later. But yes, this is what it means. So suppose I have a very connected graph and I consider the Ising model on that graph. Maybe take the, you know, complete graph and consider the Ising model on that. But you see this phenomenon in like many. You can think of the lattice, you can think of like many things. I already erased the formula for the definition of the Ising model, but you know, they basically look at e to the sum, u is a neighbor of v, x, u, x, v. This is my density. So whenever 2 points are adjacent, they want to point at the same direction. And I have this here, this beta. If beta is very big, if it actually goes to infinity, then, you know, basically the whole measure will be supported on the point where all of the signs here are either like all plus or all minus. But if beta is still quite large enough, not infinity, but still pretty large, the model will be in what we call low temperature, meaning that if I tell you that this site somewhere here is positive, conditioning only on that, I go to a very far away site in the graph, it's still going to be likely to be positive. So when the temperature is low or when beta is large, there are going to be very far away correlations in like between the, you know, indicators of different sites, even though the sites are maybe far away, okay? This is really like statistical mechanics 101, what we're doing here. We're not going to get into the details at all. And I guess Tom here can teach you much more than I can about these things. But this is really only for the sake of intuition.
So just saying it in the language of the Markov chain on this model, this is the graph itself. The Markov chain on this sign configuration, in this case of very high beta, well, let's say beta is infinity, will be disconnected.
Yes,
there is no way to
roughly this, like not actually disconnected, but almost disconnected.
But
yes,
infinity will
and
be
so right. So another way to think about it, if beta is large, to generate a point, to generate a random configuration, we first have a global coin toss, which determines whether the average spin will be positive or negative. Okay, we first kind of want to determine globally whether the system tends to the positive side or the negative side, and only modulo this global coin toss, the sides will be, you know, roughly independent, or at least if you go far away, they will not be correlated. Okay, but this global coin toss is, I want to convince you, is a real obstacle to fast mixing, because, I mean, so if we just kind of try to imagine this diagram where here we have like maybe the sum over like all vertices of xv. This is like how many positive spins I have. And this is like the likelihood. So this is the probability to find myself in a configuration with this sum, okay? If beta is large enough, there is going to be when either the sum wants to be either pretty positive or pretty negative. So the probability is kind of going to be large here and then small here, and then again large here.
That's for high beta.
This is for high beta. For small beta, I'm only going to see a unimodular thing. But for high beta, we're going to see something like this. And when I do one step of the Glauber dynamics, this is like a local update. So it's kind of like, suppose I'm here, we should imagine this thing moving in like a little random walk on this. And when it's here, there is a very large drift taking it over here. Okay, I guess the physicists here might be annoyed that usually you draw this the other way around. You think of the Hamiltonian rather than the probability. But it's like a random walk that really wants to go up and to go from here to here. It's actually going to take it exponentially many steps if beta is above what's called the critical value, where I actually see those two things.
But let me insist again on the Markov chain point of view. If you do, this is a projection of the Markov chain to the sum of the sum. If you look at the Markov chain itself, it tells
this is the discrete hypercube. This is the all ones direction. The Markov chain is going to be like the measure. Forget the Markov chain is going to be supported like on some blob here and another like one here. And here in the middle, there's very little measure. So it's kind of like either stuck here or stuck there.
If you want to give people an easy example, you can even talk about something that is completely disconnected. Imagine something like the complete bike clip or something.
Right, but if it's completely disconnected, then this is like,
but it means that you must have some problem.
That's true, that's true. I mean, it definitely needs to be connected, right? Good, I mean, this intuition is important to have as an intuition. It's clear to me that, if you haven't seen it, it's not very obvious how to establish these things, but okay.
How is this intuition telling me that there is no fast mixing?
Sorry?
How is this telling me that there is no fast mixing?
Because I mean, you kind of get stuck in one of them. So
so I'll never get to see the other one.
Yeah, I mean,
I get to.
So suppose most of the sites here are plus. You kind of update them locally, they're still mostly plus. You have to have a very rare event that lots of updates give you like a minus, even though you had a higher probability for a plus, to go from like the global plus state to the global minus state.
You also can think that you start on a delta Dirac on one of the sides, and the Markov chain starts like making a Gaussian thing around it. But at the end of the day, you want a picture that looks like that. And it's very unreasonable that it will happen fast.
Right. I mean, okay, good. So this, this is, so what I want to, yes.
Sorry, just making sure. I understand the example. I want to verify that, it seems that there is an easy fix here, right? And I don't know if I should have the easy fix in mind going forward or not.
Great. Okay, I'm glad you asked. It seems that there is an easy fix here. First, like either with probability 1/2 start from the all ones, with probability 1/2 start from the all minus ones. This indeed fixes like those examples I gave. But now let's think of sampling independent sets on a graph. So suppose you want to sample independent sets, I don't know, I don't want to draw like, just think of like a graph which is kind of pretty connected. So actually independent sets, there could also be large, like long range correlations. Now this thing is a mess, complete mess, because like, having a vertex in the independent set means the neighbors are not, but what about the neighbors of the neighbors? They're more likely to be there, but what if there are cycles? Like, how do you even guess what the global states are? Sometimes called pure states. Okay, so yeah, in this example, it's, it's solvable, but I mean, if the correlations are not all positive, even if they are, it's not always clear what to do. And I mean, even in this example, I add some external fields. So I add some a priori biases to these sites. Okay. How do they affect the total mass of the plus state and the minus state? Not obvious at all. Okay, so I mean, only in this example where everything is completely symmetric, the solution is obvious. Okay, good. So what I want to get from that is like,
well, maybe just one more comment to Lior's question. I mean, if you look at this graph, one way to see that it takes exponential time between one side and another, it's, if you think about this one-dimensional picture, you have a random walk on the line, and it is biased.
the drift here is like,
You got like, say, a 0.9 chance of going left and 0.1 chance of going right. What's the chance you'll get from 0 to n? Exponentially small. That's basically what happened.
the drift you see here is order 1, if like in the low temperature regime. Okay, good. So, okay, so ideologically, what I want to say is that an obstacle to fast mixing is the fact that there are long-range correlations, or kind of, in other words, the covariance matrix. So let's think of the covariance of mu. I mean, this is just defined to be, the matrix whose ijth entry is just, well, the covariance between is when X is distributed. Okay.
What are I and J, and what are they running on?
I mean, those are just indices. They take values in the coordinates of the hypercube.
Okay.
I and J and N. So
In 1 to n, or in 2 to, or in 2 to the n?
No, those are just coordinates.
Okay.
Just you have two sides. How correlated are they? Okay. So I claim that in the problematic cases I told you, so like non-uniqueness, this is like really a not accurate at all statement, but on a very kind of ideological level, the cases of non-uniqueness that we saw, okay, that arrow is only going this way, at least.
Wait, so what
The
is the
covariance matrix of mu, hold on, has operator norm, which is of the order of n. Or maybe let me just say, the operator norm is like much bigger than 1. Why? Because if I look at the all ones direction, I mean, all the entries are going to be, just bounded away from 0. So if I take the all ones vector, it's going to be order n if I multiply it by this matrix. Okay, so this is obviously an obstacle. I mean, again, we haven't made anything rigorous. Theologically, this is an obstacle to mixing. And the point of what we're going to talk about in the next 3.5 hours is, can we say in some sense that if you don't have this, then you actually have mixing? Are there some cases in which this is the only obstacle to mixing? Okay.
Ronen, can you explain
Yes.
again? What are you averaging there? Is nu a random measure, or
Nu is the given measure. Nu is the
Nu is the
measure
given,
of
no,
example.
nu is the, during all this talk, we have a given measure on Rn or the discrete hypercube. Okay, but now let's focus more on the discrete hypercube with our intuition. Okay, and yeah, this, for every nu, there is a matrix assigned to it. And if this matrix has large eigenvalues, then probably Glauber dynamics is not going to do too well, at least on an intuitive level. Okay, good.
Maybe another example that's more combinatorial. Again, all these examples is something as a random spanning tree of a graph. So this correlation, it was right, a uniform spanning tree of a given graph. It's a distribution on -1 to the edges of the graph. And this correlation matrix here, it just you know, you ask what's the probability that one edge will be in the spanning tree given another, right? Oh, and it turns out that there is negatively correlated. That's and that's a reason that was 30 years ago was known that on this special case, the Glauber dynamics makes it fast.
So this leads us to the this really nice framework of what we call spectral independence. Let me tell you what the kind of main thing in the framework is. The main thing is, well, a theorem that gives you sufficient conditions for mixing in terms of these covariances. But it's not enough to just have that covariance matrix is small. It's pretty easy to actually find counterexamples. The sufficient condition we're going to have is not that not only it's small, also if we pin some of the sites, we condition on some of the sites to take some values and look at the covariance matrix of what's remaining, we want also that to be small. Okay, so let's define what pinning is. So for a vector u in, so we're now in the discrete hypercube, but all of what I'm writing here will have analogs in Rn and also in other spaces. So suppose we take a vector u of -1, 0, and 1, where 0 is for computer scientists is sometimes called star, which means that we haven't kind of chosen this value. The pinning, which I denote by this curly R for restriction of u of a measure mu is, well, it's what you think. It's the measure nu conditioned on the subcube defined by this thing. So it's just nu conditioned on, let's call it the subcube S of u, where S of u is all the x in the hypercube such that xi ui is bigger or equal to 0 for all I. So if ui is 0, I don't care what xi is. And if ui is plus minus 1, xi has to be equal to ui. Just a kind of convenient way to write it. Okay. So this is just called the u pinning of the measure. Okay. And well, let me give you a Okay, I'm gonna do another definition, which is the influence matrix. Should I define it now? Yeah.
So
I
we have exponentially many such measures.
Again,
We have
exponentially many such measures. We have a lot of such
conditions
measures.
for all of them.
Yeah, we need the condition for all of them. Yeah, that's true. Let's define a matrix which is very related to the covariance matrix called the influence matrix. You should think of those two matrices as the same if you want. I mean, there is a very easy way to go from one to the other. The influence matrix at entries I and j with respect to nu is just the expectation of xi conditioned on the fact that xj is equal to 1 minus the expectation of xi conditioned on xj equal to -1, where again x is. Okay, so you know how much xi is affected by setting the coordinate xj.
Is it easier to say what it is in terms of the Fourier coefficient?
Well, the covariance is just basically the matrix of second order Fourier coefficients minus, you know, the first order terms are 2. So this thing, it's not hard to check that it's the covariance matrix times the only the diagonal entries of the covariance matrix to the -1. This is what it is. So yeah, I mean you can write it in terms of Fourier if you want. Still writing way too big. Sorry for this. Okay, so roughly, we're going to be more precise later. I mean, this is actually precise, but it's going to be a special case of the ALO theorem. If this matrix has constant order operator norm for all pinnings. So for every pinning RU of nu, the operator norm of this is O of 1 for all u in -1. Then well, we have polynomial time mixing. For Glauber dynamics. Okay, I'm gonna give a much more precise formulation of what they prove later. But ideologically, this is what you have.
The polynomial will be precise, but related to this operator, not to the.
Yes, exactly.
Yes. The exponent.
Yes. Right. Two comments. One comment is that this is a lie. It's not quite true. Because if you look, for example, but I'm basically going to give you essentially the only thing for which it's not true. Suppose that nu is just the uniform measure on all the points whose parity is like even. Then Glauber dynamics doesn't do anything. It's just stuck at one side. But it's not so hard to check that all those like influence matrices, well, they will just do nothing up to if we go all the way to a 2x2 thing. If we condition on everything except for 2 sides, then the influence is maximal. But otherwise, the influence or the covariance are very tamed. So, well, instead of GD, take GDL here, where instead of refreshing 1 site at a time, let's refresh 5 sites at a time. The number of sites we need to refresh has to do with this constant. Then everything is okay. But let's ignore this issue. this issue is also corrected if somehow the operator norm is O of 1 for everything, but when we get to really condition on many things and only have O of 1 left, it's actually strictly smaller than the maximum it could be. So there is just, you know, you just have to add some connectedness, local connectedness assumption, and then it's okay. Let's ignore it, okay? Ideologically, if all the operator norms are O of 1, then we have polytime mixing, which I think is like a really great fact. Yeah.
There is no hope for an if and only if here. Is it obvious?
It's obvious that there is no hope. Yes, but let's let's talk about examples later. For example, okay, let me give you like if you have just the complete graph and you take the Ising model, this is called the Curie-Weiss model. You have the large beta where you have two components. You have small beta where you only have one component. There is a critical beta in between where there is kind of a continuum of like the sum of spins can be anything between the minus thing and the plus thing. It's kind of like exactly the transition between the two. In this case, you have a large direction to the covariance matrix, the all ones direction, but the mixing is still okay because, you know, we took this graph that I wrote before and we kind of, I mean, we have a plateau here.
Is there an intuition why the influences will be large in this case? Or should I not?
The covariance matrix is going to be very large in the all ones direction. And the influences and the covariance are, just think of them as the same thing. Okay. Yeah, so this is one example, but yeah, there are many others. Okay, let's take questions because this is like, I mean, I really want you to get the intuition of like this thing, not why it's true, but what it's saying.
The other amazing thing is that you can prove such statements about lots and lots of Markov chains. Namely, you
right. Good. Yeah, that gets me to the second comment. We are not going to talk at all about how to prove this bound. We're just going to, there are many techniques in like mathematical physics, very deep and clever things. We're not going to touch them. We're kind of going to assume that somehow someone already did this for us.
That's not a trivial statement, of course. You got a lot.
Not a trivial, yeah.
It depends. Actually, for the big open problem which they solved in this previous paper of counting microid bases, this is a trivial statement.
That's it.
It is
I wouldn't call it trivial.
Not trivial. It's really simple. It's a simple combinatorial fact.
It's a simple combinatorial fact, but to actually realize that this is happening, but
it's a very deep. If you want to prove this, then it's an exercise for undergrads to do it in one place.
Right. So for Ising model, you can do this under what conditions?
Great. For which, on which you mean on a general graph or on a lattice?
Whatever, I mean, I know that, that Jen Ding has some results that are related to this.
Yes, yeah.
So,
we'll actually get to some of these things.
Do you need to use that, or do you have? Is there another?
I mean, I didn't tell you, on what model I'm applying this, but yes, I mean, this, for example, what you just mentioned, it's going to be useful for ferromagnetic Ising models, definitely.
Do you have do you have another technique? Is what I'm asking. Besides what Jen Ding did, it's fairly recent.
No. So like the framework what they did, and I mean, as you know, a framework to go from here to here. And what I'm going to talk about is not, I'm not going to be concerned at all with how to prove this. Okay. And I'm not going to give you new techniques to prove this.
It will be a different proof of this consequence.
Yes, of this and much more, but this is kind of like the first, So the framework is just how to go from here to here. This is
they use this high dimensional expander.
Yeah, the proof of this is based on high dimensional expanders, and maybe now okay. Let me give some more credits here, but no. This is the ALO.
You mean go from that?
Yeah.
Just that statement.
Yeah, just this statement.
Yeah.
Just this. Yeah. And this, it's very model dependent.
Yeah.
And so in their original paper, they used this to show polynomial time mixing for the hardcore model. And a very nice thing about sampling independent sets on a graph is that if you do pinning to some of the sites, you still have a hardcore model, right? You just have like a smaller graph, which so the hardcore model is actually very kind of amenable to this requirement.
And with a hardcore model, can you go up to the critical temperature or?
Good. So we'll talk more about the hardcore model next week, but yes, I mean they showed that. I mean there are many works that but yeah, already this work gives that if you have a bounded degree, you can go up to the critical temperature and get polynomial time mixing. Maybe let me just mention that this bound is highly based on techniques by what I guess it's pronounced Whites from like yeah. Let me just I'll write credits later, but usually the way to get something like this is somehow to compare your graph to a tree. And claim that on trees it's kind of not very hard.
You mean all white?
Yeah.
That's the thing.
Yeah. I'm not sure how to spell W-E-I-T-Z. So like this, he gave like they also needed to do something, but essentially is technique. Gives this for the hardcore model. Yes, okay. I think I can move on. Maybe this is a good time to take a okay, yeah.
So do I think of the restriction, the necessity of the restriction as if my Glauber dynamics are initialized on some SU that has a big side matrix, then you have no hope of mixing quickly. Like, is that the reason that you have this R in the theorem statement?
It's more than that. I would say.
Oh, okay.
It's like yeah. I think you'll have like a partial answer to that. When I show you more or less the proof. But I don't have anything clever to say about why you really need all of the pinning.
Yeah. Okay.
Yeah.
So it's somewhere between technical and not technical.
Yeah.
Okay, fine.
I mean, I'd say it's more not technical, but okay, I guess we can discuss this.
Well, basically, you can say that the proof is inductive.
Well, yes. I mean,
basically, if you think of these US subsets, right, the proof is by induction on the side of the subset.
But I mean, I think you can kind of imagine if you have a pinning with large operator norm, it's kind of an obstacle to mixing like locally in that. I mean, this is essentially what you said, yeah, right? Yeah, but it's not always, because you could like go outside of that subgroup.
Yeah, I can imagine a situation where locally it takes a while to mix, but not as long as the whole mixing time or something.
Also, yes.
But fine, I got the idea. Thank you.
Yeah. I mean, there's I think we'll just have a better intuition like after we see them. I think okay, let's take a break now, because I want to use the time to write like a few references. Like this thing it kind of started a line of papers, and it's a framework that was extended by like many other people. So I'm gonna write some credits during the break, and then what we'll do in the next hour is discuss a proof of this, which I find like simpler. It kind of relies on, I mean, it doesn't need any high dimensional expander technologies, which are I mean, they're not, I mean, if you read it line by line, they don't use a very high-tech thing, but I find them very deep and not so clear how to get an intuition for. And I think like, yeah, hopefully I'll give you more intuition regarding why this is true. Okay. כן, זה כיף. אני אוהב את העבודת האלה. לא,
זה כל פעם מנהג שלי, אני לא יכול להתחלץ על עצמי.
ממש בשמחה.
הזמן מסתכל על האנשים, אני חושב שאולי זה מרכז, אולי
לא, נראה לי הרבה אנשים לא ראו את הדברים האלה, זה היה טוב לתת כזה.
לא, מצוין. זה כל כך מעולה. So you come on Mondays. On Tuesday, it's a Tuesday. Yeah, I forgot that yesterday yesterday we just did Zoom. No, yesterday, yeah, I know, it was semester break. Okay, yeah, all right, it's the first last seminar of the week.
I was like, wait, did I forget my teacher? I mean, I did teach yesterday, but who knows?
Says 8. This one is they're not.
It's taking it out.
Makes sense because it's slightly.
Now the numbers are again 5.
What are you doing?
Linear algebra.
Ronen. This talk is recorded, right?
It is.
Okay, yeah, that's it.
Okay.
But yeah, I'm looking forward to looking at the recording. There's also part 2, right, next week?
Yeah, there is a part two.
Yeah, okay, I'll make sure I read my schedule.
I guess this was kind of a waste of time for you. But
No. It was good to see that, you know, because I hadn't seen it before.
yeah.
Am I talking on Friday?
Yeah.
Okay, so,
You're a seminar. I understood.
yeah, that's
So you run?
Kind of.
אני לא פה
בשבוע בברבדוס. שם פעמיים. יש לה אוניברסיטה במונטריאול, משהו לאוקיינוגרפיה, והם יכולים זה מאוד דרסטי כזה, כאילו לא מחר וכן. הם עושים שבוע על נושא,
עדיף בהחלט, נושאים של מדעי המחשב הרבה פעמים מלון מאוד פנסי, במקום שאף אחד לא רוצה להיות בו.
לפעמים גם וגם היו את הכנסים המפוארים של סיימונס, שזה לקח להם כמה שנים להתחיל וכמה ממש לא נורמל. המלונות שעולים $800 ליום. וזה מחריבים, רונן, אתה היית בטירה הזו בגרמניה.
כן, היה מדהים.
מדהים, אה? כן, אבל הם ניסו לחכות את דברים בביולוגיה, ממש כזה, אבל היה נחמד, ואז הם הפסיקו, אבל זה ממש באמת קיצוני. אני יודע כמה זה עולה, אף פעם לא סיפור, אבל באחד הכנסים האלה מישהו רצה להישאר עוד לילה. הוא מסתכל, ואני מבין כמה זה יעלה.
בעצם לא.
כמו חופשה שלמה. אני מניח שסיימון לא שירה, נורמלי משלמים, אבל...
שילמתי 2.
לא, תאמין לי שלא, אני... שמשאירים אותנו, הוא יודע...
הגיוני באירועים שבהם אתה...
אתה בכלל, שאתה בא, שאתה עושה אירוע גדול, ברור שאתה מקבל גם.
אם זה בא ביחד עם היסטוריה מהעולם הנושאים שלנו, או לא?
לא, בכל אופן, כן, זה משהו קשה לקרוא לזה.
בטוח שהם לא היו עצובים.
לא, הם לא היו חסך.
בסדר.
זה מאוד נחמד, אני חושב שטוני הייתה בכל נגיד 15 כנסים האלה בפעם.
צריך לעבור...
הפעמיים שהייתי, זה הפעמיים שאני הרצאתי.
קשה לקבל אינטואיציה על
אפשר לסטוני, מה התחומים הנכונים לעשות את זה? אנחנו לא מודלים קונפיגורציה.
היה
שני סייט.
כל דבר בטיסר.
בכל סייט יש פלוס ומינוס. שני סייט צריכו רגולציה. זה שאתה יודע משהו על אחד, זה אומר לך משהו על השני.
אבל
Everyone looked like Sam a little. Everyone looks like everyone.
זה מטריצה.
זה אופרטור נורם.
Yeah, I'll usually just say door and be like.
אמרתי לך מה ה-IJS שלה.
כן.
זה אומר, יש איזשהו...
האופרטור בעצם נורמה. נורמה 2.
Apparently there is one now.
זה מותמך בכיוונים של מטריצה שהיא... זה לא כזה... זה לא אופרטור נורם. כיוון
Everybody wants to take food inside.
לא, אני מדבר על כזה, על one time. זאת אומרת, אתה יודע, אם אני נותן לך לרצות A.
אמרת אם משלמים חלק
זהו, אז זה ממש מספר פולינום.
Water enclosed containers, I think they I guess one part of that works.
Yeah.
Like I feel like beverage should be some water is a beverage.
לא, אז אני אגיד לך, אני מאוד הפתיע אותי בדבר הזה, כי אין לך, שום דבר על הרעש. ומה
The first topic that I went to was CCC.
לקבל מן אמירה כזאת של דבר שמאפשר לעשות לו.
So yeah, everyone just kind of stayed outside and like stopped going to the talks. And it also happened to be when the World Cup was going on. So eventually we just had going to the talks.
משהו קצת מפתיע, כאן זה קרוב זה משהו. אני יכול לראות לך אולי.
אני מניח שזה...
Place like you finished
When you're done.
drinking.
They should put the food inside so that people are forced to attend the talk.
That's
Okay.
That works with people with social graces, but if they don't, it gets really bad.
Under the assumption.
Yeah. Steady stream throughout the talk of people.
Okay, can I continue?
Yeah.
Okay, now let's be a bit more precise in, what this means, polytime mixing, etc. So this is a very natural definition for Markov kernels. The mixing time of P is some Markov transition kernel, epsilon is some small number, and mu is a measure that we think of as like the initial measure. We start with some measure on the first point of the random walk, and then we do the random walk for t steps. And T-mix is just saying what's the minimal t, such that if you start from the measure mu, and you do t steps of the random walk, so pt, you invoke the operator p t times, so you get some measure of where you are after t steps. I want this to be close to the stationary measure in the sense that for every set A, the difference between probabilities is at most epsilon. So if you want the total variation distance between what you get after t steps and the background measure is at most epsilon.
So it's an L1 bounded, so you can.
Yeah, just an L1 bound. Yeah, and T-mix without this mu here is just I take the worst possible starting point. I start from somewhere, and I want to understand what's the T-mix where this measure is taken to be the delta just measure at this point. So take the worst starting point, how many steps do you need to do in order to get a small total variation? What's a good, what's almost not the only, okay, there are two main techniques to give bounds on this. One is by some coupling arguments. The second is via functional inequalities. And what is that? So, well, we can just take this operator and look at its spectral gap as this is a self-adjoint operator. It has, eigenvalues. One of its eigenvalues is 1, because if you take the
self-adjoint is the fact that you mentioned that it's reversible.
Reversible, yeah, exactly. That corresponds to self-adjointness. And yeah, good, thanks. And well, it has. If we take the actual stationary measure, then P of the stationary measure is itself, meaning that it has one eigenvalue, which is 1. And then we want to ask what the next one is. So lambda of P is just defined as, I can define it as a radial quotient. It's the maximum over test functions phi, which are not, how do I do it? Okay, let's do it like this. I guess minimum over test functions phi of 1 minus integral phi p phi over integral of phi square, where I only consider test functions phi which integrate to 0, meaning they are orthogonal to
but this is if nu is the constant.
No, it's an integral is d nu.
D nu.
Okay.
Okay, so this is just the second eigenvalue. It's exactly the same as what you have in graphs.
Second eigenvalue, you want to subtract, you are subtracting 1 from it.
Sorry. The difference is the gap between the first and the second. I mean, I guess you all saw it in graphs. This is exactly the same thing. If you have a graph, you have a spectral gap, there's the random walk. The spectral gap tells you how quickly the random walk mixes. It also is related to expansion. Also here, okay, I guess most of you know these shticks better than me. And if you have a bound on this, it kind of by very standard argument immediately implies a bound on this. So this is the spectral gap, and in addition we have
just for ballpark, you want this number to be 1 over polynomial to get polynomial time convergence.
Yes, yeah. So we'll yes, if this is 1 over polynomial, you have polynomial time convergence. And okay, there's another notion called the modified log Sobolev constant, which is kind of this is something about a variance. It's the analog for entropy. We'll touch on this next week. But there is a fact saying that like T mix P and epsilon is at most. So as Avi said, it's 1 over lambda of P. So if this is big, then T mix is small, times log of 1 over the minimum or points x of the measured point x. So somehow, I guess, plus log 1 over epsilon or something like that. So for epsilon constant, what you care about is 1 over this. And well, what about this? So, you know, in all the models we saw, basically the minimal measure a point gets is like 2 to the minus, order 2 to the minus n. So if you take the log, this is poly n. Okay, so if this is 1 over poly n, then all of this is poly n. Okay, good. So somehow to get this polytime mixing, what we really want to get is that you have a spectral gap. Okay, or later modified log Sobolev. Okay, so now just an interlude to give some credits for this, which I forgot to do when we started. So this theorem is, you know, as I said, by Anari, Liu and Oveis Gharan, but it's really heavily based on, I mean, it has like, it's not clear at all how to do it even given these techniques, but it's based on like very nice techniques on high dimensional expanders by Kaufman, Oppenheim, Lev Lau, and also Dinur maths and their former paper with Vincent. And this was just really a start of a line of works, which was then extended to many directions and solved. I think it gave rise to like many breakthroughs in Markov chains, and like whoever I quote here is just, I mean, it's just a partial list of people who extended this technique. And it's really the people who extended the framework. There are also many other works which, you know, gave improved bounds to like these stuff. So yeah, and this is all like, this is like, I think it was on the archive in the end of 2019 or the beginning of 2020. So it's like a very, very active field right now. Questions? Okay, so we're finally going to introduce the framework that I want to talk about. And hopefully I'll have just enough time today to kind of use this framework to reprove essentially this theorem. I hope.
So is what you're going to say today going to have any relevance to the sampling a uniform basis for a matroid using the basis exchange algorithm?
Great. So the sampling a uniform basis, it also relies on those high dimensional expander techniques, but it does not like, there's another step here to go from, so the condition there is something that has to do with the characteristic polynomial. Like there's also a notion of this is like the influence matrix. It's a matrix associated with the measure. I can also associate the polynomial with the measure, which is the characteristic polynomial, which, I mean, let's not define it now. And if this characteristic polynomial is log-concave, then it also turns out that it implies, again, via high dimensional expander things, yeah, a spectral gap.
Right, yeah, just the reason I ask is that like that particular case seems inherently tied to high dimensional expansion somehow. Just because the basis exchange algorithm is just naturally a walk on the high dimensional expansion. expander.
I agree. So this is much less, a priori, the relation is much less obvious here. And it's also, I feel like when I looked at this, I said, you know, high dimensional expander is working on this simplicial complex when there is a subsets and there is a natural hierarchy between the subsets. Here you don't see the hierarchy at all. And this is why the first time I looked at it, I said, I mean, there must be a way to look at it without, you know, thinking like distinguishing the all ones direction.
But
Yeah.
you do see
You see pinning, but
zeros are the number of things you don't fix. It gives you a hierarchy.
it gives you, but it's a different hierarchy. The original hierarchy is like the hierarchy of subsets.
If you work in
And here, which kind of distinguishes the all ones direction. And this thing does not have like the notion of subsets is not. It's a different hierarchy on how many things you condition. There is a natural way to go between the two. It's not like a very deep thing, but somehow it wasn't like, it's not so clear that you need to go through. Yeah. But anyway, this is for
Going back to Vijay's questions, so you are saying that basis sampling, for example, would not follow from this framework, or would it?
Again.
So if I want to do something like sample spanning tree, I couldn't do it using this framework.
You mean matroid basis?
Something.
You will. You can actually get, but not from this theorem, but. Yeah, I mean, it's those things are, I mean, you can kind of like describe the framework in a different way that it actually does follow from the framework. Yeah, but not from this as a black box, because like there's a meaning to the size of the sets. Like the spectral gap has to do with, it's not 1/poly n, it has to do with the size of the sets. And you don't see it here, but yeah, I don't want to get into this. Okay, good. So now let's start with the framework I want to present. Somehow I always tend to not be doing so good on time here, but what's a localization scheme? So. So first of all, let's define a localization process. A localization process is a stochastic process. Is a stochastic process that's valued with probability measures. So it's a stochastic process such that it has three properties. T1 is that for all t, t is either a real or discrete time, but let's think of it as a real parameter. Nu t is a probability measure on some omega, and think of omega as Rn or the discrete hypercube, even though it's not going to matter in most of the parts of the framework. The second property is that for every subset of our state space, if I look at this thing, which is just an, for every t I have a number between 0 and 1, this is a martingale. And the third property is that, again, for every a, the limit of nu t a as t goes to infinity is either 0 or 1. So by time infinity, for every a, we've basically, like, nu t is either completely supported inside a or completely supported outside of a. In other words, it means that as t goes to infinity, nu t goes to a Dirac delta function. It's just supported on one point.
Filtration of the martingale with respect to only to nu ta or with respect to
So nu t, the filtration is just nu t, or you can imagine you have some filtration in the background. It doesn't depend. It's a good point. Thank you. There's one filtration for all these martingales.
Maybe this needs, everybody's happy with the martingale.
Can you write explicitly what?
Nu t plus h of a given nu t, an expectation is nu t of a. For all t and h bigger than 0. If I know the measure at some time and I advance in expectation, I have the same measure. So this is a localization process, and the localization scheme.
Localization because it ends up in a Neumann.
Good. Let's yes, but it's somehow like let me just define this and then give some intuition. A localization scheme is just a mapping that takes any measure and assigns to it a localization process such that the process at time 0 is our original measure. So it's a mapping that for any measure gives me a localization process that begins with this measure and basically interpolates stochastically between the initial measure and the Dirac delta measure.
The martingale should be the result of the sample, right? It's a sample.
Again,
this limit point.
This limit point is a sample. Yes. So, I mean, the martingale property means that the expectation of nu t for any t is just nu, which means that the expectation of nu infinity is nu, which means that this Dirac, so this implies that nu infinity is a Dirac on, I mean, it could just converge to a Dirac. So let me put, so it's a Dirac on X where X is nu distributed. So I can think of it as a, very like kind of an overkill way to sample from nu. Okay. We're not going to run this algorithmically. This is just like a step in the analysis of the Markov chain. Okay, so this is the definition. Let's consider some examples. Okay, since I don't have a lot of time, I'm just going to, there are kind of many examples that turn out to be interesting, but I'll start with only 2 examples, and next week we'll see many more. So example 1 is the coordinate by coordinate. Localization scheme, which is defined as follows. Given nu, I have to give you the process. Let k1 up to kn be a random permutation of the numbers 1 to n, which will correspond to the order of revealing coordinates, and independently take a point x sampled from nu, and then define nu t as the log of x conditioned on x k1 up to x kt. So at time 0, I have the whole measure. At time 1, I generate a coordinate uniformly, and I condition this coordinate to be 0 or 1 according to the probabilities. And I kind of keep restricting the measure. By definition, since I condition on more and more things, this has to be a martingale, right? And when I reach time n, I already know which point I chose.
So here it is discrete time. It has
Here it is discrete time. Yes. Example 1, example 2.
So when you write xk1, xk2, it means acting with the permutation on x.
No, k1 up to kn is
right.
just like numbers. Each one of them is not a number between 1 and n.
That's the
It's just an order of coordinates, random order.
Permutation.
Yeah. No. All of this together.
That's a I see.
The second one is the Gaussian channel localization, which is the following. So take BT to be a standard Brownian motion in Rm. So this is going to work on every measure in Rn, but in particular on measures on the discrete hypercube, which are embedded in Rn, and define mu t to be the law of, and again, x independently take a random point according to nu, and let mu t be the law of x conditioned this time on the following thing, t times x plus bt. So I don't give you the point x, I only give you t times the point x plus noise. Now, the size of bt is like root t. So when t is smaller, most of this is going to be the noise. But when t is really large, you can actually extract the point x from this. And okay, we'll see that this is going to be, very useful for us, this type of localization. I guess it's not even very clear at this point that this is a martingale. So what you can think of, don't condition only on this, condition on all the path between condition on this Sx plus Bs for all S between 0 and t. Now it's clearly a martingale. And it turns out that, it's equivalent to just condition on the endpoint. We'll get to that later.
What do you mean by when you say law of something? You mean the distribution?
It's a measure, right? And it's the measure according to which this thing is distributed.
And it's a random measure, right?
It's a random measure because here the randomness came from this and from this. And here the randomness came from this and from this. Okay. Good. Let's just leave it with these two examples at this point. And so this so given this notion, it turns out there's a very natural way to associate a sampling algorithm, basically a dynamics, a Markov chain, with any localization scheme. So there's a natural mapping between the family of all possible localization schemes to the space of like dynamics. And by dynamics, I mean a Markov chain as a function of a measure. So let me write it like this. Given a localization process and a time tau, we can associate a transition kernel P, which will be reversible with respect to the measure nu in the following way. So via the following formula, P, the transition from X to Y is the expectation. And this expectation is over the localization process of nu at time tau of X times nu at time tau of Y over nu of X. Let me give you, okay, so let me pause for a second. So given a localization scheme assigns a process like this to any measure. Now, given the process, I can just use this formula, which gives me a transition kernel. So a localization scheme can actually assign to any measure some transition kernel, which I claim that the measure is stationary with respect to this transition kernel. Let's see why.
What do you mean by transition kernel? That's.
I mean, for every X and Y, for every 2 points in my space, I give you a number, so I get a matrix, which is it's an operator from the functions on my space to functions on my space.
The probability transition.
I should. That's the.
Yeah, it's a Markov described as a matrix.
Yeah.
The matrix of the Markov.
Yeah. So
it's not even clear that this is stochastic, but I guess
not clear that it's not clear that this is stochastic. So let's say that this is stochastic and that it's actually a right.
This expectation is just over the randomness of the localization process?
Yes, just over the randomness of, this is going to be all our randomness, like ever. Yeah. So why is it stochastic? So the expectation of, so for every X, what's the probability to go to somewhere in omega? So the expectation of nu tau X, nu tau, all of omega over nu X. This is just the sum over one like row or column, whatever, in the transition kernel. Well, nu tau is a probability measure. So this is 1. And this thing is a martingale. So the expectation of nu tau is just nu at time 0. So this is just 1.
No. Nu of 0 downstairs is not random.
No.
You're taking the expectation.
No. The randomness, I mean, nu 0 is nu. It's not random. It's a fixed measure. Okay, so this is 1. Also, if I take nu of X times P to go from X to Y, well, this nu of X cancels out with this. It's just like the expectation of nu tau X, nu tau Y, which obviously by symmetry is nu Y, P to go from Y to X. It's reversed. And the stationary measure is nu. Okay, so this is kind of a very natural thing once you have the localization scheme. And I claim that many natural Markov chains arise this way. For example, Glauber dynamics arises as the scheme associated with the coordinate by coordinate localization.
But it runs full coordinates only once.
Again?
So the coordinate scheme, just reveals the values one by one. Whereas,
So
global dynamics revisits different sites many times.
hold on, it just associates with one step. I mean,
All right.
I have to run the whole thing. I didn't tell you up to which time. I run the whole thing up to time n-1, which means I've revealed all of the coordinates except one coordinate. I have one coordinate left to reveal. And this coordinate is the one I'm going to move in. Okay.
And you repeat and you reiterate, because that's just.
And this is just one step. All of this is
and
just
if you
one
want
step.
it to, all but 5, then you can do all but L, then you can simulate what you call GDL.
Yes. So what does the coordinate by coordinate scheme do? It chooses a coordinate at random at every iteration, and then conditions on whether I'm here or here. Okay. And at some point I've conditioned on all the coordinates except for 2 coordinates. So maybe I'm like here. At some when I reach time n-1, I only have 2 points left. Right. And this formula is exactly going to be again
2 points in the Markov chain, not in the graph.
2 points in the state space of the Markov chain. Yes. You can see this is the discrete hypercube. Sorry. When there's 4 points, it is a graph, but it's the discrete hypercube. Yeah. Is it okay? I mean, it's kind of like a one-line thing, like a few lines to show it, but I don't think it will be really to show that when you do this on the coordinate by coordinate thing, you exactly get Glauber dynamics. I think, I hand waved it in a way that explains it better than just writing the formula.
And when you set tau to be n-1?
When you set tau to be n-1, yeah.
You fix the values of n-1 of the site.
And next week we'll discuss other Markov chains that you get this way. There's on our end, there's something called hit and run, and there's a restricted Gaussian dynamics that comes from this second example, and there's something called field dynamics that comes from another example that we'll see. But let's now.
This is new. This is new to your work. This localization scheme definition and
the definition and this definition is new. Yeah, I think it's kind of obvious, but it's somehow. Yeah.
Before you erase it.
Yeah.
The coordinate by coordinate. Yeah, you previously had this tau t goes to infinity. In the coordinate,
it's defined up to t goes to infinity, but if I want to associate it with a transition kernel, I only care about what happens up to some fixed time tau.
So in the coordinate by coordinate, it's not infinity. N is infinity, right? N is infinity.
That's what I'm trying to understand. So here already when you get so in the definition of the local process. You add that it should converge to a delta supported on X, which is distributed according to your initial.
This follows from the properties that I wrote, right?
And in this coordinate by coordinate, it already happens at t equal to n.
Yeah.
Yes. Yeah. So my n is in after n. Just keep doing the same thing. Yeah. Good. Okay. I mean, it doesn't. I mean, it's defined up to infinity, but just extending it in a stupid way.
But
okay.
So for the main theorem, you'll prove it when this stops at some n-L, where that L depends on.
Yes.
The over.
I mean, you can basically. I mean, you get something up to, for any n-L. yeah, this like kind of regards to the comment we did before that sometimes you don't take the one Glauber dynamics where you take the L Glauber dynamics where you refresh L sites at the same time. This corresponds to taking tau to be n-7. Yeah, very good. Okay, so now what is this good for? I think some stuff I'm just gonna write and prove the next time. I mean, all of this is very easy to do, but I mean, takes a bit of time. So it turns out that it's very easy actually to see. It's just a few lines of direct computation that the spectral gap associated with with the transition kernel that comes from some localization scheme and some time tau is just equal. This is just a direct computation to the following thing, to the minimum over all test functions phi of the expectation, again, with respect to the localization process, of the variance with respect to the measure nu at time tau of the test function phi over the variance with respect to the original thing nu, measure nu of phi. So this is just equality. You get this immediately from the definitions. That's just
what's phi running on? What is phi?
Phi is any test function from my state space to R.
So I should think about it as a vector getting vector on the hypercube or vector.
Yeah, like vector, like the vector is like indexed by points of the hypercube.
It's a function.
It has 2 to the n entries.
It's a function on the hypercube.
I see.
It's a vector of the dimension of the probability matrix.
It is states. It's like its coordinates are
The other
different.
states, yeah, exactly.
This is our state space omega, and there is some function phi defined on our state space. Okay, it's oscillating in some places. And there's the initial measure nu on omega, and we start running this process. The process kind of localizes in space. At time 0, it's like over the whole space. And as time progresses, it kind of zooms in, it keeps zooming in, and at time tau, maybe it has zoomed in all the way here. Okay. And what we want to establish in order to say that there is a spectral gap is that even after zooming in all the way up to time tau, we still see some variance in the zoomed in measure. So it's not, we want to say that it's not the case that even though the function over all of the measure has like lots of oscillations, has a big variance, it's not the case that locally it looks almost constant. You zoom into some local thing and you still see some of the variance. Okay, this is what you want to argue in order to say that there is a spectral gap. Okay.
But why do you have alpha there? P alpha tau?
This is L. This is the localization scheme.
Okay.
Okay,
Yeah.
so if you want to prove mixing for Glauber dynamics, you want to say you run the coordinate by coordinate localization, and you don't lose a lot of variance. And well, now comes a very natural thing to do. We have a process, and we want to say that by time t, we have not lost a lot of variance.
T will be n-1.
N-1, but you know, this is general framework, and you can take anything. A natural way to give a lower bound for this is to say, let's just do one step, go from t to t plus 1, or if t is continuous, go from t to t plus epsilon, and say that the variance has not decreased too much. Okay, so definition.
But with t equals n, there will be no variance. So it doesn't.
Again?
So when t equals n, there is no variance.
Right. Or in general, when t equals infinity, you've already wasted or you've burnt all your variance.
It has to be like very gentle. You want
Right,
to say n
right,
minus
right,
one steps,
right.
it's still
Yes, yes. You want to say if you didn't get all the way to the end, you didn't waste all the variance. Yeah, very good. So definition, the process nu t satisfies epsilon approximate conservation of variance, meaning it almost conserves variance if, well, for all t and for every test function phi, maybe let's say up to time t, up to some time capital T, so for every t less than capital T and every test function phi, we have that the expectation of the variance with respect to nu t plus 1 of any test function given nu t is at least 1 minus epsilon times the variance with respect to nu t of phi. And I want this to be almost true. So I want to say, take any time t, take any time, any test function. When I do one step of the localization, so this is in discrete time. In continuous time, we'll have a different natural version of this. Well, I didn't lose so much of the variance that I had. Okay.
Just as a sanity check, when tau or t goes to infinity, this lambda goes to 1, right?
What is lambda? No, lambda, the spectral gap.
Yeah.
No, to 0.
Isn't
the variance you have left goes to 0 because you focused on one point.
You're going to get the same. Nu t is going to nu t when t goes to infinity
goes to a delta.
The expectation is over tau.
Like you have like the variance over a Dirac delta of anything is 0. Okay. Good. So this is, you know, a kind of a natural thing. And
it's a Dirac of at a point which is distributed according to nu.
It's no nu becomes a Dirac. It's Dirac on a random.
Yeah, it's a Dirac, which I mean it's a random Dirac measure, but it's a Dirac measure. So, and the variance, this inner variance, yeah, sorry for that. This inner variance, this expectation is with respect to the localization process. This inner variance is like it's a function of this and this.
The new infinity is a Dirac delta on a random x. The expectation is over x. The variance is over the delta. So the variance is 0 because of delta.
I see.
So you need epsilon to be a function of n.
Yes, yeah. I'll need epsilon to be like 1 over poly n. And then I can, okay. So I don't have a lot of time. So let me kind of hand wave and I'll see, maybe I'll do one thing today. But yeah, if I have, so now if we have this bound, then we can get a bound for this by a telescopic product, right? I mean, if we have epsilon approximate conservation of variance in one step, then up to, so this basically will imply that lambda of the original thing is, you know, at least 1 minus epsilon to the power tau, right? This is, I mean, just take the telescopic product, okay?
That's, so lambda is still the gap or lambda is the eigenvalue?
Lambda is Lambda is the gap. The gap, it's very small, but it's hopefully not too small. So, okay.
No, it seems like if you get epsilon to be polynomially small, then you can make it a constant, which is unlikely.
Right, good, yeah. So what we will actually have is that you will have epsilon sub t here, and epsilon kind of and epsilon looks like kind of like 1 over n minus t.
Like in the analysis.
Like, yeah, exactly. So this is all kind of the same in this sense, only this analysis does this, localization martingale, and their analysis kind of embeds this into a simplicial complex and goes in the layers of the simplicial complex. And in both cases, you get some product. We will see this next time. In both cases, you will get some, what you actually get on the right-hand side is something like the product I1 to n of like 1 minus, and this thing is like the operator norm, eta I, this is very bad eta I is the operator norm of what you have after the pinning over n minus I or something like that. And if this is a constant, then this product is like only polynomially small. And well, the question is the whole question is how to get a bound like this. And it turns out that when you do the localization, there is a family of localization schemes such that these bounds kind of very naturally follow from bounds on the operator norm of the covariance matrix. So can I take 3 more minutes? Just kind of a teaser for next time. Yeah. Trying to also do the next thing, but so what we're going to have is, and by the way, this part of the proof is actually very similar to what happens in the KLS conjecture and what you do for log-concave measures. Like the idea of like that the covariance matrices suddenly arise, this was exactly this way was already there. So there is a very natural family of localization schemes called linear tilt local. I mean, this is what we call them in this paper. So what is a linear tilt localization? It's just a localization scheme that to get from the measure nu t to the measure nu t plus 1, you multiply by a linear function. So it's localization schemes such that nu t plus 1 of x over nu t of x to get from the measure time t to time t minus 1. This is equal to 1 plus, this is going to be the last formula that I write today. It has this form. Again, it could be continuous time, but this is the discrete time version. What's written here is the following. So B of nu t is just the center of mass. Nu t. To get from the measure at time t to t plus 1, I multiply by a linear function, which is equal to 1 at the center of mass. By doing that, I'm not changing the total measure. Like the integral of only this part, no matter what zt is 0. So I keep it a probability measure, as long as this side is not negative, of course. And I'm going to choose it so that the expectation of zt is, or the expectation of zt given nu t is 0, meaning that this is a martingale step. I'm adding to my measure something that has expectation 0. So this is a vector with expectation 0. And, I can choose a bunch of vectors ZT here. I can do many things. This gives me an infinitely rich family of localization schemes. And it turns out the coordinate by coordinate localization scheme is of this form because pinning is like multiplying by a linear function that's equal to 0 on one side and equal to whatever it needs to be equal to keep the measure on the other side. Okay. But also I could take ZT to be the increment of a Brownian motion, which gives what's I guess now called stochastic localization. So it's kind of an infinitesimal linear tilt update. Okay. And it turns out that for this family, whenever I have this a formula like this, it's just there's one small and dumb application of Cauchy-Schwarz that shows that the derivative of the variance of any test function is related to the covariance matrix. And the reason is it's related, I mean, at least on an intuitive level, you multiply by linear functions. So this is kind of a moment generated.
Is that bracket? So what is that bracket? Is that just a dot product?
No. It's
a dot
product. Yeah. Just this is a vector. This is a vector. Just a dot product. Yeah.
Is there 2 to the n vectors?
No.
Vectors in
It's just for any time t, I have one vector in the space Rn. Ct is in Rn.
Oh, 0, 1.
I mean,
but it will be an Rn because they
Rn, I embed everything in Rn
because you need to center of mass.
Yeah. Exactly. Everything is in Rn.
Isn't x the same as the x inside the nu?
Yeah, I mean, R to the.
This is a function of x.
So x is a point in omega.
No, x is not a point. It's not a state. It's a point in the X is a point in omega.
X is a state.
Yeah, x is a point in omega which is embedded in Rn.
Omega is R to the 2n.
No, the size of omega is 2 to the n. Yeah, sorry. Okay, so just to hand wave one more minute. This is kind of a moment generating process in a sense, like we multiply by linear functions so that time differentials of quantities will correspond to moments. And it turns out that the time differential of the variance, which is a quadratic quantity, which is like, quadratic quantity will correspond to some second moment in space because the X appears here. And I mean, that'll just be bounded naturally by the operator norm of the covariance matrix.
These are some moments in some weird randomly chosen basis. ZTs give you some kind of
yeah, I mean, I can define ZT to be whatever I want.
Yeah.
Right? Any ZT will give rise to some localization scheme. Okay, I mean, ZT is some adapted process of vectors, okay, which can be like infinitesimal or not. Okay, so next time we'll see how it actually works. It's actually very short, but this is like the main ideology behind this. Okay, questions?
All right, thanks. Questions? Okay, good. So we are going to lunch. So ask questions at lunch before we have time, before the food runs out.
I get a free lunch.
You get it?
So I'm happy to do next week.